perspective without the complications of investment planning and long-term planning, but we're looking at an operational setting first. As you have seen or heard from the announcement, as I mentioned before, this slide I'm going to show every time. This lecture is recorded on Zoom and will be made available on the ISIS course afterwards. So maybe let's go back to this one slide that I showed in the last week in the lecture on hydro storage or hydroelectricity more generally. And one important component for assessing the kind of resource or the potential of a potential run-of-river site would be how much water actually flows in a year through the location where you are considering to build the run-of-river power plant. And of course, the overall volume of water plays a role, but also here the time series of the water flow plays a role. We saw in another chart here that there are certain constraints that if the flow is too high, you may be not able to use everything. And then if the flow is low, you may be required to reserve a certain fraction of the kind of average flow or median flow, save that for environmental reasons to keep that in the natural river stream. So, but one big question or one big prerequisite to do this water flow resource estimation would be the calculation of this catchment area. And as you can see in this other illustration here, this catchment area depends on the elevation data. So a input data set that we would use for this is a data set that lets us know about the elevation, because then we can compare, for example, in a rastered data set, the height differences between neighboring pixels and calculate in which direction would we see the flow. So one assumption you could make, for example, that the water would flow in the direction of the steepest descent. And actually this kind of height data set, so elevation data set, would be more or less sufficient to get a rough indication of the catchment area, as you basically calculate the area that is encapsulated by the ridges of a system. You can find these kinds of data sets online. So there's this most popular hydrosheds database. So these are prepared catchment areas here for river systems in South America. And you can go into kind of various levels of details where you can see these kind of, the parts of the river that then accumulate like a tree to the pour point. So if you take the bottom left here, for example, you would have water flows kind of towards the northeast. And if you have if you measure the water flow here, this would be water that comes from this area. And basically, we want to do now this in Python to calculate this catchment area ourselves. So let me switch over to the notebook, which you can also follow on the course website as regular. And compared to many of the other tools that we've used so far, it's more of a niche tool, I would say. I don't think it has too many users. So it's not as broadly distributed as pandas or geopandas, for example. It's a relatively specialized use case, for example, also like AdLight. So this Python package does not really anything else than calculating the catchment area. So the area that drains into a specific point based on a so-called digital elevation model. So elevation data set typically represented as a raster data set. And so what we're going to need for that is definitely one raster dataset for the elevation. And then we're going to step-by-step build this elevation model or the catchment area around it. So as many Python packages, we'll start with some fundamental data structure that kind of manages the data inflow and the functions. In the case of pysheds, this is an object called grid. And we'll also reuse a couple of functions that we know from earlier tutorials from matplotlib, numpy, and cartopy. The digital elevation model, you already know how to read in raster data, and this is also what pysheds will do in the background, just with a slightly different syntax. Namely, we could reference our file name, and importantly, this is one of the Python packages where you can't directly read in from a URL. So this is why initially I downloaded the TIFF file and can't pass directly the URL here. So there's again a two-layer process here where we build a grid from a raster file. Our no data value would be 0. And also we then read this raster into memory with the same settings to give us a digital elevation model. So DEM I just chose as abbreviation for the raster data for the elevation. We can plot this. So this is nothing new. I think we've done something like that before. Just gives you a broad, rough overview of the area that we're looking at. We're looking here at an area in the north of Portugal, where it's a bit where it is a bit hilly, and then we have kind of the ocean here. Kind of that should be a good test in the end whether the water flow drains there ultimately. As many data sets, we have the problem that they don't always come completely clean. And what we need to build this catchment area is that we need a system that completely drains. So in the hydro literature, this is called a digital elevation model that fully drains, full drainage. So that's the ability of the water to flow from any cell to the edge of the digital elevation model. And that's a prerequisite for this hydrological analysis. So pitfalls that happen here regularly are pits. So these could be, so if you imagine just the elevation model and you have a pit. So a raster cell that is surrounded by cells that are higher. So we would have water flowing into that, hypothetically. But the functions that we're using, they don't really know that the water would fill up and then eventually go somewhere else. So one thing that we need to condition this digital elevation model is that we remove pits. So these would be single raster cells where every surrounding cell is at a higher elevation. So basically, if we have this case, then we would just lift the elevation or correct the elevation of this one cell in the center to the kind of lowest surrounding cell. And then there are a few more items here, depressions that are just kind of groups of cells that are surrounded by cells at a higher elevation. So that's just pits in bigger. And then flats can also be a problem if you have a really large area where you don't have any elevation difference. Then you also don't have clear water flows if you follow this approach, for example, to say the water follows the path of steepest descent. So these have to be dealt with. Pits and depressions, you just lift basically to the lowest surrounding cells. And for the flats, you introduce a very flat gradient and make some assumption about how the water flows. So there's basically a function for each of these steps: fill pits, fill depressions, and resolve flats. And these will give you new grid items, each of them, that are then kind of passed to the next step. So we can execute them. Some of them take a couple of seconds to do. I think it was 20 seconds or so. And then based on this conditioned digital elevation model, we can compute the direction of flows. No? Okay, well, it's already 30 seconds, but we can continue while it's calculating. So the next step here would be computing the direction of flows. And these will be necessary to kind of calculate how the flows from the upstream river accumulate into the river towards our pour point, the point where we look at how much water flows there. And there's a value scheme, so-called D8 routing scheme, that assigns kind of floating or integer point values to certain directions. So if you imagine a raster and then you have 8 different directions, right? If you consider all the surrounding raster cells around them, you can go north, south, east, west, and then you have the diagonals northeast, northwest, southeast, southwest. And each of them get assigned a value that is then processed later. There are other routing schemes. This is one of the most simple ones. I think the values are chosen so that you get, I mean, it's kind of it's kind of 2 to the power of 1, 2 to the power of 2, 3, and so on. And it's, I think one nice feature of this is that when you do this, so calculate the flow dir, the flow direction, and plot this, then you get something that looks a bit like a relief 3D, 3D outline of the elevation. Good. So basically what we now have is that for each of the raster cells, we have a value of 1, 2, 0, 1, 2, 3, 4, 8, 16, 32, 64, and 128 for each of the 8 directions. We have a few values of -2 and -1, and these are just cells where the flow direction could not be determined, and that's typically the case at the boundaries of the area that we look at. So especially here, you can see a little bit of weirdness, and that's just the coastline where it is a flat, but it doesn't have any further orientation points kind of next to them in this data set. So the flow direction cannot really be determined. Good. So what we can do now is we take okay, we take or we look at one particular raster. Oh yes, thanks. 0 would be, I think 0 is one of the directions. Oh no. No, so then 0 would be also a no data value, which we initially specified here. Yeah. Okay, so how do we now calculate the flow accumulation? Basically, by having the flow direction, we have now established a relation of which raster cell flows into which other raster cell. So we can kind of backtrace if we have one particular raster cell we are interested in, where we think we could build a run-of-river plant, for example, we can backtrace which upstream raster cells feed into this pour point just by looking at the directions. And this function here, accumulation of the flow directory of the using the flow directions, it will do exactly that. It will just count the number of grid cells that contribute into any one cell. So I'm not sure how well this will be visible to the online community, but I'll try my best to make it as large as possible. So say we're interested in this point, and we know, and I'll now just use arrows for the flow direction, which are represented as values. Then we could have something like this. Something that looks like this. So we have something like a ridge here. And we can now look which cells go into this cell, where we have this cell going here, this cell going here, and well, no, that's not true. We have this cell going here and this cell going here. So we definitely have two cells contributing. But if you think about where does this cell end up, well, it flows into here and eventually into this cell again. So we have another cell contributing. And if you think about this one here, this will also go into this one and eventually end up, sorry, it should have been like this, and eventually end up here. We could also, so we have a value of 4 for this cell. So that's the accumulation 4 if we are just counting the number of cells. This one has 2 cells contributing to it, and each of these in the area that we look at have just 1 cell contributing to them. And these values, 1, 1, 1, 2, and 4, these would be the accumulation of flow. Yes?
Say for the cells that basically where a stream has its origin, there's 1 cell contributing. But then a cell that itself might have a stream as an origin as well, plus another stream going in. It only has 1, because like the cell down in the middle.
Ah, yes. Yeah. So I. You,
5 at the end?
Yeah, so you're right. I made one mistake. So from this, so if you think about this raster cell, we get 1, the cell itself, here. For this cell, we have 2 contributing cell plus the cell itself. So it should actually be 5 cells that are contributing.
2 cells contributing plus the cell itself?
There are, I mean, in total to this flow.
Middle cell.
Yes.
It says 2 currently.
Yes.
But that only accounts for the cells.
Yes. So we have this one. We have these 2 plus 1 gives the 3. Yeah, so that's right. So another way to start is just maybe that, and maybe that would have been easier, to start with the kind of cells that sit at the ridge. You give them a value of 1 because they only contribute to themselves. And each cell definitely has 1 because it's their own area that is covered. And then for the cells that accumulate, they get the cells that contribute to it plus themselves. So here we have 2 cells contributing plus the cells itself is 3. And then for this one, we have these 3 contributing, 1 contributing, and another one that is itself. So, I mean, this is a simplification here because, I mean, if I could now take these 5 and say this is the amount of water, but what I didn't consider so far is that different cells might have different levels of rainfall, especially if you have bigger systems. So what you would do in reality, if you wanted to calculate the flows here, you would do you would not just count the number of cells contributing to that, but you would just kind of sum up the flows that you measure for each of these cells. Yeah. So how can we calculate the catchment areas? Well, we just look at all the cells that contribute to this pour point. Yeah, so this one here might go somewhere else, and these also go somewhere else. Yes. Uh-huh. It's just a hypothetical example where you maybe have a ridge, and then towards one side you have the flows going in one direction, and then you have the flows going to the other direction. That just depends on the the elevation. Okay. So one thing that we can do now, once we have this accumulation, and actually we can okay, doesn't exist. Anyway, so this ACC object, it's a raster object. It's not really a NumPy array, but it's very similar. It's probably using that under the hood. But you have now here some cells, for example, where there are 392 raster cells contributing to that. And we can now use, based on this accumulation, because the accumulation, the cells with very high accumulation are basically downstream in the river. They have high flow, so you have the different estuaries contributing to that. And the values of ones, they are basically at the ridges, at the outskirts of the catchment areas. And there's a function that lets you specify a pour point, so just some coordinates that I know are inside the raster dataset that we're looking at. Before we calculate the catchment area with the catchment function, we need one more step, and that is the issue that we can now specify a cell, but maybe landing just next to the high accumulation point. And there's a snapping function that just looks for the closest raster cell that exceeds a certain number of upstream cells included. So it looks for a cell that is closest to my test or trial pour point, but that has this condition fulfilled that it has at least 5,000 upstream cells contributing to that, so that I kind of match or hit the river and don't have this accuracy, for example. So if I have this river here and different estuaries contributing to that, then I might, because of some inaccuracy, pick a point here that is not on the river. So my flows here would actually be quite low. But what I'm in many cases then looking for would be actually a dam here. So we would kind of snap this point to the closest one that has high flows. It's just a small utility function. You can see if we look at now the coordinates x snap and y snap, that they will be kind of relatively close to the original trial coordinates. So it's 0.01 degrees of variation here. Yes? Yeah, it could be from a different data set, for example, where someone gave the location of an old run-of-river power plant, and they gave the coordinates not for the location where the dam would be for the run-of-river plant, but where the power station of the power plant would be. So you can have some inaccuracy there, especially if you have coordinates from different data sets. Of course, if you know exactly where the pour point is and where the dam is, then you don't need this snapping function. Yeah. So what we can do now is to calculate the catchment area. So we just pass our x and y coordinates here, as well as the data set on the flow directions. And there's different ways to specify that. In this case, we're just providing the coordinates. Good. So what we can do now is we can kind of focus on our calculated catchment area and clip that and basically exclude everything that is not part of this catchment area and calculate the flow accumulation for that part and then plot that. And we get kind of our river system. I'll show you in a moment how I plotted this, but you can see now how you have this pour point. This would be our coordinates that we were looking for. And you can see, especially similar to the hydro basins example I showed at the beginning, that you have here kind of different smaller rivers all contributing into a bigger river at the location where we now have the pour point. And we can now do things like calculating the general area of the catchment area. And if we combine it, for example, with this ERA5 reanalysis dataset, we can look at, well, this catchment area, in which raster cells of the weather data does it lie? What are the statistics about the rainfall, the evaporation, and so on? And then calculate basically daily water flows at this point, which we can then later use for calculating the power production potential of a potential run-of-river plant at that with a dam at that red point location. The plotting is relatively similar to the plotting that we've done previously with raster data. It uses this imshow function for presenting rastered data set. But the setup is a little bit more complex for the scaling here. So we have, as coloring, we have the number of upstream cells and on a logarithmic scale, because this is how you can see something in this chart, and otherwise you would just have a strong dominance of the kind of downstream river cells compared to the initial estuaries. So what we do here is, yeah, we do some cleaning and just look at the catchment area, just look at the catchment area and keep everything else white. The color map here is a cube helix color map. That's just one of the standard color maps here with this color scale. And then what we can do in this imshow function is we can specify a norm, and here we can specify this log norm, which then lets us plot a logarithmic color bar. Okay, any questions so far? Good. So I would say we take a short break then, maybe just 5 minutes, because this is already all that I wanted to show for pysheds. It is a relatively straightforward package. It doesn't actually have too much more functionalities. There's some more functionality about kind of layering different catchment areas onto each other that you can also see in this hydrobasins example, where, of course, basically you could calculate a catchment area for each of the pore points. And in the hydrological literature, what you will often see is that you will calculate catchment areas or pre-built catchment areas for the locations where one river flows into another river, and then you have kind of a hierarchical system of river systems. And in terms of hydroelectricity systems, what you would have something similar if you do the modeling really properly, where you establish a relation between the kind of a flow relation between the hydroelectric plants, where you have maybe one run-of-river plant upstream, maybe even with a reservoir where you store water, that where a downstream run-of-river plant depends on the control of the upstream run-of-river plant. So you can layer the catchment areas onto each other, where then the kind of the dispatch of the upstream run-of-river plant determines the water availability in the downstream river plants. So it's never just about one catchment area, but kind of it's a layered system. You would do that for every run-of-river plant, and of course you can have more run-of-river plants in one river, and yeah, that's all I wanted to say. Question? Yes, 2 questions. Okay, good.
One that specified bidding, right?
Yes. Yes.
So can we also use this to make an estimation on the water flow rate, for example, or
Yeah. Yeah, the whole point of that is to estimate what the water flow would be. It's kind of the first step. Kind of once you've determined what the area is, you can overlay that with a different data set where you have, because here we don't have any data about the actual rainfall or water flow in the rivers, but we have the kind of, yeah, the catchment area, so the area that feeds into that node. And then we can look at the weather data for this area, which might come in a different raster at a different resolution, and then can look at, from that build, how much water we have, and typically that is done at a daily rate, for example. So unlike for wind and solar, where we have typically hourly resolution, we would look here at kind of daily flow rates. Yeah. For really big systems, kind of one more complication would be to calculate delay in the flows because the flow is not instantaneous. So if you have really many layered systems, then you can have kind of delay in the water availability as well. Okay, I'd say take a short break and then restart with the next Python package in 5 minutes.